Okay, hello there. My name's Luke Jennings. I'm VP of Research for Push Security, and I'm here today to talk to you all about Phishing 2.0, particularly detecting tools like Evilginx, EvilnoVNC, Muraena, and Modlishka. So, moving into the background, why are attackers adopting new phishing tooling and techniques? That's the first question for us to cover. So, the main reasons for this is essentially we've got a situation now where most organizations have adopted MFA over the last decade, and we've also had the creation of the EDR market, which has made endpoint attacks increasingly difficult. So traditional phishing attacks were either credential harvesting focused, so gathering the password, or they were sort of based on malicious attachments and compromising an endpoint. Now, MFA means that gathering a password on its own is not necessarily as useful as it was previously, and endpoint attacks are becoming harder as well. Now, the other aspect is that cloud identities are increasingly the target of phishing attacks, because now that we have lots of SaaS apps in use by different organizations, we often have, say, an identity provider acting as an SSO portal, and that one portal will then enable access to lots of different apps. Additionally, we tend to have local identities present on other SaaS apps that aren't going via SSO as well, so they are also good targets for phishing attacks. So we're seeing a sort of an evolution in security controls, and therefore changes in how phishing attacks are conducted. So what do the stats say with regard to this? Well, there's a whole number of incident reports out there that address this in recent years. For example, the recent CrowdStrike report noted that 80% of the attacks they tracked involved some sort of identity attack and compromised credentials as part of that, so it's a very common part of different breaches. And Verizon have noted also that stolen credentials are like the most common way that web application breaches happen. And in terms of gaining access to credentials, even if you're not doing the phishing attacks yourselves, there is a criminal underworld supporting this, and more than 1,000 credentials appear each day on the dark web marketplace, and that's generally happening for the majority of those in less than a day of them being harvested. So we're definitely seeing a lot of phishing attacks still. Now, Okta more recently have then said they've seen an unprecedented increase in credential stuffing attacks, so reuse of those credentials, and the Tycoon two-factor authentication phishing as a service platform is using attacker-in-the-middle phishing attacks at scale as well. So we've seen over 1,000 domain names detected between late October and early 2023 and early February 2024. So there's lots of stats to show that there are changes happening here, as well as the control situation haven't changed. So why are anti-phishing controls traditionally failing then? So one is that if we look at more proxy-based phishing attacks now, as they've evolved into to try to get around things like MFA, well, EDR as an effective control as it is for endpoint-based attacks, for those types of phishing attacks, we're not really seeing anything happening on the endpoint. There's no malware delivered, so it's really just an interaction between the user's browser and the phishing site itself. And that makes it very hard for EDR to discover that. It's just not suited for that. It's the wrong tool for the job. So it becomes a little bit of a blind spot. So as we've seen sort of move away from some of those endpoint compromise focused phishing attacks, EDR is not as effective at seeing sort of proxy based phishing attacks, or just traditional credential harvesting phishing attacks. The other aspect is that a lot of people tend to be reliant on sort of threat intel feeds for new phishing services and like domains and IPs. There's nothing wrong with doing this. If you find valid attacks through doing that, that's fine. But it's very difficult for TI providers to keep up with this. Attackers are generally spinning up lots of new domains and switching between IP addresses, and there's now more sort of increasing use of shared IPs and shared domains and that kind of thing. So it's very difficult to maintain an effective block list for this type of thing. It can obviously serve a purpose as part of a wider strategy, but it's certainly not something to rely on its own. But we're also seeing sort of content-based controls increasingly being bypassed as well. Attackers figuring out ways of evading fingerprinting techniques, and also like web-based obfuscation like HTML smuggling is sometimes being used to get around proxy filters and that kind of thing. So there's a range of reasons here. Phishing's never been easy to detect anyway, and some of the sort of more traditional methods are now failing to deal with it. So when we are talking to people about this problem, we normally sort of see two statements coming back. So organizations that think they are perhaps less vulnerable than they are. So if we're talking about phishing, normally we'll hear, don't worry, we've got MFA. And the second thing we'll normally hear is, oh, all of our business apps are behind SSO. These are two separate things, but they're obviously strongly related, since SSO normally will have an MFA component. And there's also nothing wrong with these two things. They're both good things to be doing. It's good to be having SSO, it's good to be having MFA. The difficulty is that the reality in the modern world is that, like, we often see fewer than a third of identities are actually using MFA. So for a start, there's often lots of cloud identities outside of SSO portals that aren't actually using MFA, so it's not protecting those. The second thing is, I think some people sort of consider MFA as a protection against credential harvesting phishing, but really the evolution of phishing into sort of proxy-based attacker in the middle techniques has meant that this is no longer true. So the most common forms of MFA that people use, such as SMS or one-time passwords or push notification-based methods, they are phishable. It's just that they're not valid for a long period of time, but attacker in the middle techniques are intended to deal with that problem, and we'll see that later. Now, passkeys, if some of you are familiar or are using them, they are designed to deal with phishing, but realistically right now they are literally less than 1% of MFA methods used that we see. It's not, they're not common, and of course they're going to increase in popularity as time goes on. But I think we're looking at a long time before that becomes anything substantial. And then there are other problems to deal with, like, do apps, which apps support them, and are there fallback methods? Because there are disadvantages to having things like hardware keys or other tokens. So, particularly when things are lost. So often people, even if they are using them, will allow a downgrade method where a user can pick to say, try another method and then use a one-time password. So like anything, they're not a silver bullet. And they are not used much at the moment. So most organizations effectively, even if they're using MFA, they're still highly vulnerable to phishing-based attacks. And with SSO, well, what we found is fewer than a third of apps out there, like SaaS applications, support SSO. And many of those that do only have it at, say, a premium tier for the licensing. So you may want that, and then it's like, oh yeah, of course you can have SSO. We'll just double your license cost, which is quite a difficult business model. I mean, if you're in a position there where you don't need any other features, you're happy otherwise, you just want SSO, and then organizations are faced with like doubling or tripling the cost of a license, that can really off-put organizations from using that feature for something that should probably just be standard at any license level. So in addition to that, like, organizations that we see typically have at least 100 applications, if not more, in their estate. So when you've got a large number of those that don't support SSO, you're in a situation where, okay, SSO is good, but it really is only protecting probably a minority of applications. And in addition to that, 1 in 3 employees we find tend to reuse passwords, which often includes reusing the password they use for their identity provider in other applications, which introduces another risk. If they are phished or compromised another way, they can be then reused against an identity provider. So at the end of the day, these are good things to have in place, MFA and SSO, but I think people often think they're much more effective at dealing with this problem than they really are in practice, and as such, phishing just isn't going anywhere anytime soon. So, a single secure identity. I sort of alluded to this before. What we commonly see when we look at organizations, when we deploy and do SaaS discovery, for example, is from initially speaking to them, we'll be aware of a bunch of apps that they use, that they've indicated. They'll have a few dozen apps that central IT have configured to put behind SSO, that goes via their identity provider. So they've got some secure authentication mechanism they're using for that. But the reality is when we deploy, we tend to find it's a much different situation. There is a harsh reality here where there are a large number of other apps that are in use within the organization, typically self-adopted by employees, and therefore aren't necessarily using SSO. And so that means they may also not be using MFA, there may be shared passwords involved, so we end up seeing hundreds of apps overall, and really then thousands of sprawled cloud identities across them. So therefore we have a situation where the sort of, the way the organization thought the situation was with their smaller number of apps well protected behind their SSO is not really reflective of reality. Many apps not only can't support the SSO, but they weren't previously even aware that they were in use across the organization. Okay, so moving on to attacker in the middle attacks, and we're starting with phishing via proxy-based techniques. So what is this? So as I said before, traditional phishing techniques were either based on harvesting credentials in a login form normally, or delivering some kind of malware via an attachment or a link that has some sort of file download. Now MFA made this less effective for the credential harvesting part because generally the second factor would have a very short lifetime. So gathering a password on its own was only half the picture. So attacker in the middle techniques are based on solving this problem. So they sit in the middle and they proxy a connection in some way between a victim and a legitimate end service. So say you were using Okta as your IDP. It could be sitting in the middle, proxying the connection, and it essentially means then that it will enable the login mechanism to operate as it should do against the legitimate service, which means that it will accept a password, then it will produce a prompt for an MFA factor, and the user can enter that too. And then the end result is a successful login session with the session token stolen that the attacker can then reuse. So it's designed to get around MFA for that. Now, it's essentially an alternative to info stealers for stealing sessions as well. So that avoids endpoint attacks. So one other way that we see sessions being stolen and MFA bypassed is through info stealing malware on endpoints. So that's one way of getting them, but this is a way of doing it without touching the endpoint. So we're going to look at two different methods of doing this. Sort of attacker in the middle is one example that tends to be using a web proxy technique, but there's also a slightly different version, more of a subset of this, called browser in the middle, and there's some slightly different advantages and disadvantages, so we're going to look at both of those. So essentially, how does it work? You'll see the victim will access a malicious URL, then the traffic will be routed via the attacker proxy server to the legitimate website. Let's say it was Okta as an example here. They enter the credentials. If they enter the wrong password, it will, the real site will be able to validate that and say the passwords are wrong. Whereas if they enter the right credentials, they will be accepted. So it will behave exactly as they would expect. And then there would be an MFA request, and let's say it's a one-time password. The user can then enter the one-time password, access will be granted, and at that point the attacker has access to that authenticated session. They can take the cookies that they've intercepted over the wire there and import them into their own browser and hijack the session. That's how it works. That's basically the sort of high-level picture. So what tooling is out there for this? There are a number of tools. I'd say like three of the most common kind of open source tools that you could find on GitHub would be Evilginx, Muraena, and Modlishka. Evilginx is probably the most common one that's updated the most, but essentially they all serve similar purposes. They can proxy multi-domain destination traffic. They'll encrypt and decrypt TLS and perform modifications, and then essentially do the proxying and steal the sessions as they go. So they're quite similar in how they operate. Now, just so you can see what it looks like, we're going to use Evilginx as an example here. So we're going to see what it looks like when compromising a MFA-enabled Microsoft account. So without further ado, let's start on the video demo. So what happens here, we'll start out, we have on the right, we have the attacker's Evilginx session, an SSH session that's running, it's been enabled. And what we've got is this domain, login.pushdemos.com, where we are proxy into Microsoft's own login servers. So as you can see, that looks like a Microsoft login. And that's all set up ready to capture sessions. So on the left, effectively, we're emulating the victim. We're saying they've already clicked a phishing link, and here they are. So they go and enter their username. So I enter my test username here. I'm then prompted for a password. I enter my password. This will be validated correctly by Microsoft. So we've already captured that. We can see that on the right. And then I'll be prompted for my chosen MFA method, which in this case is a one-time password using Microsoft Authenticator. Evilginx has now continued to proxy all this. I'm now logged in, and as a user seeing that, I'm now logged into my legit Microsoft 365 session. I would see all the files and emails and other things I'd expect to see because it is legitimate. But from the attacker's perspective, they've stolen the session. I can list it here. I've got the password as well. The tokens have been captured. And if I want to now, I can just dump those tokens, import them into my own browser, and hijack that session. So that's using Evilginx to bypass an MFA-enabled Microsoft login. We could do it with any site. I've just used Microsoft as an example here. So, what are the pros and cons of this type of attacker in the middle technique? And this is probably the most popular one. And the advantage is really, I think, that it's highly scalable. So it's using standard web proxy techniques, which have obviously been developed for decades, to be highly scalable and reliable way of proxying connections, and they've just been used for an offensive purpose. So it's quite easy to set this up and use it to handle lots of different users coming in for phishing attacks, handle all those connections concurrently. And it's rendering everything exactly as it would render in the browser. It's acting as a web proxy, so everything behaves as you would expect it to behave. So it's very useful from an attacker's perspective from that perspective. One of the disadvantages is that there is a little bit of a cat and mouse game going on now, where for the major application vendors out there, it's in their interest to try and stop this from working, right? And there are techniques that you can put in place as an application vendor to try to make this more difficult or to detect new instances of it occurring. And typically these involve just laying sort of tripwires in your application code, for example, in your HTML and JavaScript. So putting things in place that factor in the domain that's being accessed in some way and use that as either a silent detection technique or making it actually actively break a login, like making it part of a crypto exchange during the login process that means it won't work by default if it's accessed on an incorrect domain. So if I'm on like attackerdomain.com, that may interrupt the login process, or some JavaScript code may notice that and then send a silent request off somewhere else to report that it's maybe an attacker in the middle technique. And that way the vendors can then discover people using phishing attacks, maybe work with law enforcement, maybe report them to other TI vendors and so forth. So there's a little bit of a cat and mouse game going there for the major vendors, and then obviously the tool developers are finding new ways to bypass this. But there's a different set of pros and cons for another technique, which shares a lot of similarity, but is a little different, which is called a browser in the middle technique. So we'll look at that now. So for a browser in the middle technique, it's very similar, but it goes one step further by, rather than using an actual web proxy for proxying the connection back and forth, really it uses EvilnoVNC as a library to essentially remotely control a browser. So what happens is the user, when they access that malicious URL, they are actually just being proxied to a VNC server, and they are graphically controlling the attacker's browser without realizing. And that means they are literally directly logging into a site on the attacker's browser for them without realizing. So if you imagine, this is literally the virtual equivalent of if I was an attacker sitting next to my victim physically in a coffee shop and I handed my laptop over to them with like an Okta login page and was like, do you mind logging in for me please? And they went, certainly, sure. And they logged in and I said, thank you very much, and took it back. It's the virtual equivalent of that. You're literally logging into the attacker's browser for them. So we're going to look at one example here called EvilnoVNC, which is another open source tool for this. But yeah, a lot of these techniques use VNC as the basis, and the NoVNC library is one that enables that to work on the web. So there's lots of legitimate purposes for this as well, but in this case this is just an offensive use of it, and EvilnoVNC is one example of these tool sets. So we're going to use this now as an initial access attack for compromising an Okta tenant this time, to give a different example. So similarly to before, the attacker is on the right and the victim effectively is on the left. We've already clicked a phishing link, and you can see I'm on this definitely not phishing.com domain, and I'm looking at an Okta login page. And in this case, this is effectively the victim's real Okta login page, but it's just they're actually looking at an attacker's browser instead without realizing. On the right, we have the attacker. We've got their terminal session running EvilnoVNC, but because that's really just controlling a browser, we're going to bring up the attacker's browser as well, so we can see both instances of it, the real one and the rendered VNC version on the left. And what this means is that everything that the victim does is mirrored, because they are really just controlling the attacker's browser. So you can see as I enter my username there, the attacker sees everything that's going on, and they can monitor this. And we've got the same process again, where I log in with a username and password, and then prompted for MFA. In this case, I'm using the Okta Verify app, and I pick the one-time password method and enter that, and then I'll be successfully logged in to Okta. Now at this point, the victim on the left sees all the normal applications they expect to see in Okta, because this is their legitimate Okta tenant, so it looks pretty legit at this point. If they haven't realized something was up by now, then they're probably convinced everything's fine at this point, because they see what they expect to see. Now, from an attacker's perspective, I might say, okay, I've got what I want now, and this might not be the most stealthy way of doing it, but I could just cut the user off. So there I go, just disconnect them. It looks like the app stopped working to the user, and all I say now as the attacker is, right, thanks for logging me in. I'll take back my browser now, thank you very much. And then I'm in. So at this point, I can start looking at post-exploitation options. For example, if they're using Okta SWA, one simple thing is I might just want to start grabbing some other passwords for other apps that are configured in there and using those and noting those down too. And they don't go through the SSO mechanism, so they might be a way for me to laterally move afterwards. But if I'm happy that this is all done, I could keep using that browser, or I can eventually tear down the connection and look at what other data has been captured and is available. So we obviously still capture the data we see going through it, just like we did with the other technique before. So we've still got the password as well, and of course we've got the cookies, so we could use them to import into another browser later if we want to. We're going to see that shortly. Okay, so what's the pros and cons of a browser in the middle compared with what we saw with a proxy-based attacker in the middle techniques before, like Evilginx? Well, the advantage is it's resistant to some of those security controls we looked at before, because the reason is it's really difficult for an application vendor to do anything about this, because there's no standard web proxying technique going on. From their perspective, a browser is directly accessing their site without a proxy in place. There's no way for Microsoft or Okta or Google or whoever to know that the browser that's accessing their site is actually secretly being remotely controlled through a VNC session by a different user. It's just not, they're just not in a position to be able to observe that. So it really gets around some of the common tripwires and techniques people have been put in place to stop attacker in the middle techniques. That's one massive advantage here. But like everything in life, there's disadvantages too. And I think the disadvantage for browser in the middle, and probably the reason it's maybe not used as commonly, is that it's a scalability issue. Essentially, you need a VNC server to support each connection while it's going on, which people tend to deal with like Docker, multiple Docker instances being redirected to and spun up and down. But it's just more difficult. It's It's not as easy to do as having a web proxy based solution. And the other thing is, it's obviously very different to a real web app. It might look the same, but if you start interacting with it, or certainly if you view source of the page or do anything like that, you'll realize straight away that it's very different to the real application, because actually you're interacting with a graphical rendering of a screen rather than with a normal HTML-based application. And that can cause other problems. Even simple things like changing the size of the browser window while you're on it may cause issues with render resolutions, and then you may see a distortion in the rendering, which can spoil the illusion. So there are downsides, of course, too. Okay, so now what? We've looked at the initial access phase, and that's generally what people focus on and think about first. But there's another step from here which is really important with where phishing attacks are going now too, and it's the post-exploitation phase. When compromising cloud identities in particular, the potential blast radius of a compromise is really large, it's huge. And I think attackers are specifically targeting SSO apps, especially like Microsoft, like Okta, for this reason. I think traditionally, when we see evolutions of new attack techniques, like what we've seen in the past, is that it starts out with the initial access part, and once people figure out that, a large amount of the focus then becomes about post-exploitation. How do you get the most out of every compromise? And I think that's something that has really changed quite a lot now and is quite concerning and is a really important part of the puzzle going forwards. So, for the next demo, what we're going to see is post-exploitation with basically persistence techniques and lateral movement within Okta. So I'm going to say, what can someone do once they've compromised just a normal user, not an admin user, but like a fairly ordinary user of Okta. So in this case, we're going to follow on from the demo we had before. We're going to assume at this point the attacker's just re-imported those cookies into their own browser. So now we've got a full screen window that is just the attacker for these post-exploitation techniques. So the first thing that I want to do is laterally move to lots of different applications. And that's the best thing about applications like this, is you can immediately move to lots of downstream apps. And then even if someone detects and kicks you out of the Okta account very quickly, you've established legitimate sessions on lots of downstream apps that probably won't be cancelled when that happens. So that's the first level of lateral movement and persistence. In this case, I'm going to show it happening with Shortcut. In this case, Shortcut is using an Okta SWA login, so it's essentially just logging in with a username and password for me, which we can also steal. But I'm now logged into this app, so I've moved here already. And now I'm looking for some way to persist even further. And there are lots of very simple techniques with different SaaS applications to enable this. So here we're going to look at one example, just simple API tokens. Any ordinary user here for this application can create an API token. I go and create one here. That means even if I get kicked out of Okta, even if I get kicked out of Shortcut, my session is cancelled. I've got this API token I can use to come back later. So that's one persistence option. I'll then move to Google Drive, where, okay, what we're going to say is that in this case, we've compromised a finance user. That's the idea. So I've gone to their Google Drive using a similar technique. Okay, how do I maintain access here? Finance, that's probably the most interesting thing this user has access to. I'm going to make a sharing link. We've all used sharing links. They're designed for sharing things with external parties. They're also a very effective and simple persistence technique. So I've made that sharing link. Now that folder is shared, and as an attacker, even without access to the account, even if I'm kicked out of all those things, I can come back via a direct link that I've noted down in future. So that's another simple technique at the file-based level. And then we'll see a third example here. I'm going to go, oh, we've got to Expensify. Okay, just an expenses app. How do I maintain access here? Are there any simple techniques? Okay, this supports secondary logins. This is something I call, as an attack technique, ghost logins. We can go and add in our own Gmail account. And then this is another common feature in SaaS applications. That means I can then log into this app using a different email address I control in future. So even if I get kicked out of the Okta account, or kicked out of that email address that the user normally has, I've got my own Gmail account there to gain access. So we've seen effectively, very quickly and easily, laterally move into 3 downstream applications and setting up 3 other simple persistence-based techniques just from one single standard user compromise. We're now going to look at something slightly more advanced using a technique called SAML jacking. So what we're going to assume here is that though we haven't compromised like an Okta admin or a general sysadmin or anything, they're not admins of Active Directory or Okta or anything like that. They're a finance user, but it's common when you've got hundreds of SaaS applications in use in an organization for there to be application owners. So in this case, maybe Expensify is an app that a head finance user might have admin control of, even if they don't have that for sort of core systems like Okta. So we find they're an admin in this case, and it's been configured for SAML-based SSO via Okta. And SAML jacking means we modify this SAML process. So SAML effectively means when you go to log into an app, it redirects to a different URL. And that happens during the login process after you've already seen the legitimate application URL. And so from a user's perspective, the original link looks legit, and they're expecting to be prompted for credentials. So if you can redirect someone to somewhere malicious, it's a pretty convincing social engineering attack. And in this case, we're going to use SAML jacking to turn that into a pretty sneaky lateral movement technique. So we're going to go and look at the configuration that's already been set up to allow authentication via Okta. So this is my Okta bug crowd instance. I'm just going to go and replace that, and I'll put the same URL that I used for my EvilnoVNC attack before. So I'm changing that to my phishing URL, and I'm going to save that. And what this means now is that any other user that decides to access Expensify via Okta is going to get automatically phished. I don't need to send them a link. So if I go back to Okta now and I click Expensify, what you're going to find is it takes me to Expensify, requires the email for the SAML login, and then immediately redirects to my Okta phishing page as well. And a lot of users are going to fall for that, like even very security conscious users, even security professionals themselves could easily fall victim to this attack. And at that point, you can spread your infection to other users through this as a watering hole based technique. Okay, so hopefully that gives an idea of why the post-exploitation phase here is so important, so dangerous as well. So imagine from an incident responder's perspective, it's very difficult to deal with as well. This is not just like an old school endpoint compromise where you just take it off the network if you catch it early. You've got a lot more to consider in terms of downstream apps and persistence options. So I guess at this point, we're just going to summarize now with the question of like, so what? If we're talking about phishing attacks, some people might just say, well, phishing isn't a new threat. It's been around for decades. Of course it has. Access should be temporary, particularly with MFA. And access can be revoked if it's detected. And we've been responding to like Active Directory compromise for years. Has much really changed. So I think the point here really is that SSO, although it is a good thing overall, if you do manage to phish SSO credentials, it increases the risk of compromise because it enables you to laterally move and gain access to so many other things from one place. The other aspect is that because we've got so many SaaS applications in place, and we went over before how you can't use SSO for all of them, you can't use MFA for all of them, it's actually much harder to stop general credential attacks against lots of applications like that, or even have visibility of it. It used to be that people had one VPN endpoint, one webmail endpoint, and that's the only place they had to worry about authentication and putting the controls in place and the monitoring in place. Now, someone could be phishing for your SSO and also phishing for other apps, also stealing credentials from elsewhere and then replaying them against 100 different other SaaS apps. And it's very hard to detect all of that. So this is something that's really just got a lot worse. We've really kind of moved backwards from a security perspective in this area. And then the sort of incident response side is now very different, as you've seen before. Even for effectively a low privileged user account being compromised, we've got a lot more to think about in terms of containment and responding to a single user compromise. We can't just take an endpoint off the network, reset an account, and then do some forensics separately. We've got to think about every downstream app that they might have moved to very quickly and whether any different persistence mechanisms could have been established on those. And this is really only the beginning. I showed you doing this manually, but as I said before, what we've seen with evolution of attacks in the past is that once the initial access side changes, post-exploitation often becomes the focus after that. So I think very much post-exploitation automation is coming. And when these types of attacks start automating the movement and persistence of 100 different apps, we're going to see a very, very different risk profile with these types of attacks, something that's much worse. So the question is this the new C2 framework? So I've got Evilginx, Metasploit, and Cobalt Strike listed there. And I think yeah, this is a personal opinion, but from my perspective, like Metasploit and Cobalt Strike radically changed attacks of their eras, and they started out with initial access focused and then became very post-exploitation focused. Evilginx is in its early days in some regards, but I think is becoming a sort of de facto tool for these types of new techniques, and I think it's very much going to become the tool of its age, or at least one like it, even if it's not Evilginx. I'm using that as an example here, and I think in particular we're going to see a lot more post-exploitation coming, and it will be a new tool set we see used regularly. Okay, so how do you defend against this? Look, it's not easy. You probably guessed from this, like defending against phishing has never been easy, and this is an evolution of that. So we can't expect magic solutions here. Yeah, there's a couple of things you can do. Like I mentioned, that for the sort of proxy-based techniques, we see sort of custom JavaScript being used. Application vendors do this sometimes themselves, but if you have your own websites or intranets, you can implement similar techniques. You can also use things like custom CSS for your own Microsoft Azure tenants, Entra tenants, and so forth. There are ways of deploying this to other shared tenants too. And there are providers out there like Thinkst, with their Canary tokens. They have ways of doing this in quite a nice packaged way as well. The other thing is to keep up with general TI. As I said, you can't rely on this completely, but if you've got decent feeds of known bad sites, then you need to consider these new techniques in those and rolling that into your existing systems. Also, updating IR playbooks is another important thing. So I think, arguably it's one of the most important things. An SSO account compromise is a very different situation now than a standard endpoint compromise or just a single account compromise. And they need to factor in all those different lateral movement and persistence techniques to really look at how far a compromise has spread and how to contain it effectively. So that's incredibly important for incident responders. I think also you just need to introduce controls to try and detect phishing toolkits and cloned websites. So we can't rely entirely on TI, so we need more generic techniques here. And now that we've got new tool sets being used as part of phishing, we need to think of ways to introduce controls to detect tooling and to generally just observe websites that might have been cloned from your identity provider or another target. Now the other thing is, I mentioned passkeys before. Passkeys are very good for dealing with attacker in the middle attacks specifically, but there are some other problems to consider there. Right now they are hardly rolled out. That will increase. But as we've seen before, we've had MFA in general for 30 years or so, and still today there are organizations without MFA or with only partial MFA. So these things do not happen overnight. There are downsides to them as well, although they're very effective at preventing this. There's always an operational and management overhead. And then obviously, it's what applications support them. So maybe you get it in place for your SSO portal, but as we know, SSO can't be applied to all the apps you're using. MFA can't be applied to all the apps you're using. So it's never going to be a perfect method on its own. But these are the kind of things that overall, putting them together, is how you look at raising the bar for attackers to jump over when attacking your organization. Okay, so I'm going to just show you a little bit quickly about what we're doing with Push, how we're trying to help in this space. So we have a browser plugin for a lot of what we do. So I'm just going to show a couple of features where we're trying to raise the bar a little bit, because I think with some of these attacks right now, the bar is on the floor, and it's about getting those first steps in place. How do we detect some of these tool sets in use? How do we generally make phishing become harder? So we're going to see a couple of things of that. So I'm going to start with just showing some of the things we're doing for blocking and detecting attacker in the middle and browser in the middle toolkits. So very briefly, before we actually go to our controls page for the push tool, I'm just going to talk conceptually, at least at a high level, about how we do this type of thing. Broadly speaking, we're looking for any evidence of difference between a legitimate site and behaviors that we would expect to see for attack in the middle approaches or techniques or tool sets themselves. I'm just going to use EvilnoVNC as a good example again here, because this does all sorts of things, so it'll give a better idea. this is just, say, the HTML page for a legitimate Okta instance. So we can see the DOM as it's been loaded. So being in a browser extension, we have the benefit of seeing everything. Like once it's loaded, we see how it changes in response to user events, as well as all the network traffic and everything. So effectively, we can inspect and trace activity in a lot more detail than you would with something like a proxy. But this is what the DOM looks like when it's been loaded. If we then look at an EvilnoVNC example, although it may be visually similar, it is clearly different in terms of the HTML. So I've selected that canvas element, which Chrome has just highlighted. That's why there are those squiggly lines on the left. But you can see how it may visually appear similar to a user, but even just the HTML at this level is completely different, as well as many different things that are different in terms of what happens in response to different user events. So there are lots of different approaches for different techniques and tool sets here, but this is just an example. We're looking for behavioral differences, and the browser extension is in a really good place to deal with that. So we'll move on to the actual tooling we use to detect it now. So this is our controls page, which hosts our ITDR features. So we've got a few things in place here at the moment. We're going to focus on these first two. So right now we're going to look at the phishing tool detection. And essentially, I just want to show some of the features of that if we load that. Now we have different settings. So what we're doing here is in our browser extension, we can observe everything that's going on in the browser, everything's loaded, what's happening in the DOM, how the user's interacting with that. It gives us a lot of power for looking for evidence of malicious activity. So we are putting it in different modes to configure. So we've got warning mode here. There are multiple modes. So we can just obviously disable this, or we can have it in a monitor mode where it just simply reports up findings to the system, which then gets forwarded onto your SIM, and you can see that's a security team, but the user wouldn't see anything. Or we can have warn or block modes where it will actually directly alert the user as well. So in warning mode, they'll be able to bypass it if they want to, and in block mode, they won't even have that choice. So I'm going to show you what that looks like. I'm going to use warning mode, and we'll see what it looks like as an example here with an Evilginx test. So let's go to our user's browser. Let's say they've got a phishing email, and so they're like, okay, I'm clicking this link. They load that, and then you saw the initial page load occurred, but as soon as our browser extension has observed the full DOM load and everything and determined that actually this looks like EvilnoVNC, it's kicked in and given this warning. And as warn mode, they still have this button where they can proceed anyway. But otherwise, this is a strong warning for the user. Now, that will then report an event back up to our system, and that will be reported to your SIM if you configured webhooks as well, so you can get those centralized alerts too. So that's what we're doing at the browser level for phishing tool detection. We're going to move on to a demo where we detect and block attempted SSO credential reuse. So this addresses another part of the problem where rather than detect tooling in use, we're going to try to stop SSO credentials being reused. So essentially we want to pin someone's password for their identity provider to that particular identity provider tenant and make sure they don't use it elsewhere, which is a very sort of generic and effective control, at least for the password factor, for your most important asset being your SSO endpoint. So in this case, what we're going to see is we've got this, this potential phishing page, and our user is about to log into it. Now, if I just enter a password, like just literally the word password or any other password, it's fine. But what happens here is when the browser has a k-anonymized hash in place to know what the IDP password is, which you can check locally. Like we don't synchronize those things, but what happens is it can detect if that gets entered into a field. So in this case, when the user actually goes to try to enter that IDP password, our browser extension immediately kicks in, and before the form's even been submitted, it redirects the user here, indicates what's happened. It'll also then, like we saw previously, fire up an event to our system too, and if you've configured webhooks for your SIM, that's where those events will go, so you'll get a notification as a security team too. So those sort of two controls combined provide some pretty good protection against these phishing attacks. Okay, further reading. So obviously most of this webinar has been about phishing and evolutions in that. We saw a couple of product features just of what we're doing at Push to try and help here. But obviously in the post-exploitation phase, I really spoke about quite a lot more. And I went into a whole bunch of different areas. If you're interested in the much wider space here of identity attacks and where they are moving and how that SaaS apps play a role in that, then do check out the SaaS attack matrix. This is sort of culmination of a lot of other research that I've done. It's on GitHub, so it's an open source project here. But it's kind of inspired by the MITRE ATT&CK framework, but focused purely on sort of new age identity and SaaS focused attacks. So if you're a red teamer or you're a blue teamer and you're not aware of this project, but it seems interesting, please do go check that out, see if it's of use for you on your next red team or in terms of enhancing your security controls as an organization. So definitely check that out. And okay, that's it. That sums up the webinar. Thank you for listening.